Thank you, Linda. Okay, let's start a little more discussion on steel design. So, few aspects of steel structure, some of them we have already discussed as part of the advantage of steel structure. So, one point, we already know that steel is stronger than concrete, and therefore we can construct larger or stronger structures, right, with steel. So it is the ideal material for modern day construction. Modern day construction, it means to say that when we are looking for taller buildings, steel will be the preferable material. Why? Because the strength is approximately 10 times that of concrete. Okay, it is much stronger than concrete. That is why if we are going for a large span bridge or a very tall building, then steel will be preferable. Then, because its large strength to weight ratio, okay, for a same amount of concrete, the steel will be much stronger if the weight of the steel and concrete is same. That I mean to say that if the quantity of material of steel and concrete is same, obviously the steel is much stronger. It can take much higher load, and therefore if we are going to construct a very tall building or a very large bridge, then construction with steel may become economical. Okay, in general, steel is costlier, but if we are going to construct a very large building where a lot of material will be required, in case of RCC, but if we use steel, because it is very stronger, we may use less material because the steel is stronger. The requirement of sizes of columns and beams are smaller. If we are going to construct something, for example, if RCC column required is 500 mm by 500 mm, the steel will be required maybe 200 mm by 200 mm. For example, I'm saying, so that means the quantity of material will be required much less in case of steel construction, and therefore in the entire construction, steel may become economical only if the constructions are very large or tall buildings. Okay, then another point we discussed, construction is very fast. If we want the structure to open for public use or private use, whatever, quickly, then we should go for steel construction. Another important point, we did not discuss this point, that steel structures are ductile and robust, and it can withstand severe loading such as earthquakes. Now we already know the fact that concrete is not ductile. Incorporate reinforcing beams into concrete for its ductile property to make it able to withstand or tackle earthquake forces, wind forces, etc. These horizontal forces are supported. We have to provide reinforcement. Only then these horizontal forces can be supported, right? We know that already. So the steel structure, when it is entirely steel, then it performs much better in case of earthquakes, because this entire structure is now ductile. It is steel, it is going to behave as a ductile material. Now, steel structures can be easily repaired and retrofitted. If some part is having some damages, we can do welding, etc. This type of thing, or we can add some material bolting. We can remove a damaged bolt and install another bolt. Things like that we can do very quickly. And steel is also eco-friendly because after the use of this structure, if it becomes that this structure is not in use anymore, or we have some extra member that is not required, we can dismantle a part and it can be reused in somewhere else. Then another important concept is what is the life cycle cost. Okay, the life cycle cost will involve, life cycle means the lifespan of a building. If we are going to design a building, we will say that this building should last for 80 years or 100 years. That is the lifespan of the building. Okay, similarly for other structures are also lifespan. It is a part of the design procedure. Now, what is the total cost? Okay, because the total cost will involve the cost of construction, repair, maintenance, dismantling, everything. Okay, this entire cost in the entire life cycle, in these entire 80 or 100 years for a particular building or structure is the life cycle cost. Now, in case of steel structures, what may happen, the life cycle cost, the total cost of construction, maintenance, repair, dismantling, etc., concrete structures. Why? Because the maintenance is easier, repair is also easy and quick, and if we dismantle it, we can sell the dismantled items, or we can reuse it in somewhere else, right? So therefore, there is higher value even after being dismantled. So this entire added up life cycle cost can be less. Then we talked about better quality control. This we already understand because the steels are produced in the factories under controlled conditions. They are bound to have better quality than RCC, which is prepared at this site by most of the time unskilled people who do not have all the technical knowledge required, and they go on to do something which will affect the steel are prepared in the factories. There are preset standard um, requirements, etc. Therefore, the steel products are of better quality. Then, in this advantage, we discussed that steel is less fire resistant. So what we have to do, we have to do something special, covering special protected coat, etc., to resist corrosion and fire. And they should be designed in detail for easy fabrication and erection. Good quality control is required for proper fitting when we will be fitting them in the actual structure. To ensure the proper fitting, we should take care in the quality control in the production stage itself. And effects of temperature should be considered. Then these are some points. You go through those points. I do not have to go through all the points. You see it later when I give it to you. But one important thing we should remember, the carbon. Okay, the addition of carbon in steel. What happens? Okay, if we add carbon, the strength goes on increasing, but the ductility goes on decreasing. So that is one thing that we should remember. So in the previous PDF also, there are some points about the production of steel. Please check it. Then the production, in the production stage, there are different types of production. Some is called hot rolling productions, rapid cooling production. This type of, there are ways. Okay, the cooling rate of steel from I should have written one word here, from this temperature at which it is being produced in the factory, then to room temperature produces different microstructure, and that imparts mechanical properties. So the way we will cool the steel, will give it different types of properties. Okay, so that's why we have different types of steel. Okay, that's why we have TMT bars, thermomechanically treated. So these things are coming from this concept, how we are treating the production of the steel element. Okay, structural steel sections are produced by hot rolling sections. Structural steel sections are those I section, C section, hollow sections. Those are structural steel sections. So they are produced by hot rolling. Okay, the process of rolling. I will show you later the proper diagram, which involves temperature range of Austin 10. Now, these things are not much required. I have given to you for your reference. Okay. When they are allowed to cool in air, which is called normalizing, what happens? They gain the mechanical strength. Okay. So that much is important for us. Okay. When they are allowed, they increase, they gain the mechanical strength, and the way they are allowed to cool will depend how much mechanical strength and ductility, etc. properties are developed in our steel element. Okay. Then there can be another way of rapid cooling. Okay. If we do that, what happens? Uh, martensite is produced. Okay, the martensite is very hard but less ductile. So this procedure will make it very strong, but the ductility will reduce. Then we have stainless steel. We all know about stainless steel. So it is an iron chromium alloy. We should know that. About 11% of chromium is added, and the resulting steel is stainless steel. This is because at this minimum level, what happens? A thin protective passive film forms on the steel, which acts as a protective layer, and therefore it is resistant to corrosion from outside agencies. So these are some other more points. Please go through them later. Important point is stainless steel is costly, but again the life cycle cost can be less. Why? Because it is more durable. Okay, because it is resistant to corrosion and etc. It is going to be durable. The life cycle cost, the entire cost of from production, from installation to our maintenance, repair, everything involved, the entire life cycle cost of the structure will be less or maybe less. Therefore, the stainless steel is increasingly being used in our constructions, even though per unit cost is more. Then, coming to this graph is stress strain curve for mild steel. We have seen this graph a number of times. We already know. We'll just go through it briefly. Okay, the initial portion, it is proportional. The stress and strain is proportional. On one side we have stress, and one side we have strain. What is stress? What is strain? We know it. I don't have to explain again. I know. Now there were 2 points. This was your upper yield point. This was your lower yield point. We will consider our yield strength corresponding to the lower yield point. Okay. This point here will be our yield strength, stress at which the steel yields. Then this will go on increasing a little bit more. There will be an ultimate point where the strength becomes maximum, and then it decreases, and then it finally fails. Again, and this is the ductile region after being yielded. How much extension may occur in the steel element is its ductility. If this portion is more, that means the steel element is increasing even after yielding. The element is increasing in length. Okay, it is not breaking down. That is our ductility. We know that. And yeah, this one we have discussed. Moving on, this one. This one is stress strain curve for high strength steel. Now here the curve is like this. In the earlier one we had like this, there was a definite point of yielding. We know that, okay, this is the point of yielding. Therefore, the stress corresponding to this point is our yield stress. But now we do not have a definite point of yielding. See, we do not have a definite point of yielding. We do not know where exactly yielding is occurring. So what we decided that there will be one procedure. We'll say that if this is 0.2 percentage strain, that means strain is 0.002. Okay, it is much strain. At that strain value, what we will do, we will yeah, at that strain, from that strain, we'll have a straight line which will be parallel to the initial portion of the stress strain curve. Okay, the stress strain curve is going like this. Initial portion is straight line, and after that, this occurs. Okay, so we'll saying that from a region of 0.2 percentage strain, which we call proof strain, from there we will have a straight line which is parallel to the initial portion of stress strain curve, and then whatever is the point this straight line meets in the stress strain curve, we will be calling that as our yield stress. This point becomes our yield stress. Okay, so this is called proof stress. This stress is called proof stress, and then this strain is called proof strain. Okay, and this is offset method. So when we have a definite yield point, we will use that definite yield point for finding out what is the yield stress in the material. And when we do not have a definite yield point, we will use the proof strain to find out what is the yield stress for that material. Fine. Then the design concepts you have already discussed. You know already what is limit state method, what is working stress method. The concepts are same only. But one thing I want to discuss here, what is characteristic strength and what is characteristic load. Okay, the both is required. Strength is from the material point of view. The material is strong enough or not, and the load is from the structure point of view. The structure is supporting what load? What will be the load coming onto the beams and columns of our structure in the lifespan of the building? That is characteristic load. Okay, basically. Now the definition, characteristic strength of a material such as concrete or steel is defined as that value of resistance below which not more than prescribed percentage of test results may be expected to fall. Okay, so if we are testing a material, 100 units of material, and there has to be a particular strength below which 95 percentage of the results should not fall. Okay, for example, if we are testing cubes for M20 grade of concrete, that means we should get a value of 20 Newton per millimeter square compressive strength. Now we are testing, for example, 100 cube. So 95, at least 95 of the cubes should have value 20 Newton per millimeter square or more. Okay, only 5 percentage are allowed to fail. 95 percentage of the test should pass the minimum value that we have assumed it should have. Okay, then only it is going to be the characteristic strength of that concrete or steel or any other material. Fine. Now what is characteristic load? Now the load which will not be exceeded 95 percentage of the time. Okay, we are in a building, we are saying that the characteristic load column on this beam is, say, for example, 3 kilonewton per meter square. If I am saying that, then in the life cycle, at, at least at 95% of the time, this value must not be exceeded. So that is characteristic load. So both these is important in our design procedure, because from the characteristic load, we will know what load is coming into the structure and what should be the strength of our beams and columns and the structural members, right? And then we will decide what should be the characteristic strength of our beams and columns, etc. Fine. So both these are very important from design point of view. Okay, and this may be different in some material, but for concrete and steel, this is going to be, for our purpose, this is going to be 95%. So remember the 95%. 95% of the time, it should pass the test. Then only it is characteristic strength. Then we go to connections, okay? Because we are studying steel, the elements are coming from the plant. Now these elements will have to be connected at this side, and then only we will get a structure, right? There has to be some ways of connecting. Okay, and I will discuss it detail again. So first, bolted connection. So these can be different types of bolted connection. Okay, so here I have one plate, one steel element, another steel element, and another steel element, and these steel elements are connected by a bolt here. Okay, so this is called concentric connections. Why? Because the load is coming in this direction, another load is in this direction, another load will be in this direction, or another member force will be in that direction, and they all are in the same point, they all are going through the same point, right? They all are meeting one single point, and therefore it is called concentric connections. Here also we have one plate which is connecting the members. Okay, this element, we have some bolted connections here. The axial force is acting like this. Here also we have some bolted connections. The axial force is acting like this, and they are meeting at one point. And in this member also, axial force is here, and they are all meeting at one point. And therefore we are saying that these type of connections are concentric connections. Fine. Then this is another member. Okay, here I have one element, and here I have another element, and they are connected here by bolt. These are bolts. Okay, these are bolts here. These are the bolts from one side, and from the sectional view, this is the view. So here what is happening, this is the load, and this load is producing a moment. Obviously we know that, we understand that that moment is being produced here at the connection, right? So this is called a moment connection. Then this type of connection, this is called shear connection. Okay, lap joint, there is one plate here, the other plate is above this plate, and then connected by bolts, single layer of bolt. Then this is double bolted, there is two layer of bolts. Okay, same thing, one plate here, one plate above, and connected by bolts. Okay, so here what we can have, because the plates are at different level, one force will be here and one force will be slightly over that force, right? The axial forces. So there will be an eccentricity, there will be a distance between the two forces. So this is eccentricity in the lap joint, and due to this eccentricity, the plate ultimately may go like this. Okay, because the force is not at the same plane, there will be some moments generated, and that moment may lead to this kind of uh, deformation. Okay, couple I should say, not moment. Then in the same shear connection, this type of connections may also be there. What we are doing here, we are connecting the main plate with a cover plate. This is a cover plate, and then we are bolting the main plates with the help of cover plate. We're connecting it with one cover plate, so single cover. If we are connecting with two cover plates, then it is double cover joints. So this type is called shear connections. Why? Because if the forces are here and here, they are going to produce a shear on the cover plate. They are going to produce a shear on the cover plate. Say, for example, the force is acting here and here in this way. What they will do? They will obviously give one shear here, right? So that is why it is called shear connections. Now, the connections are very important for any structure and they are designed more conservatively than others. Why? Because the connections are complex. The analysis is complex than the main members. Why? Because there are a lot of balls, there are a lot of directions in which the force may be acting. Therefore, the analysis is complex, and any discrepancy between analysis and actual behavior is large. The discrepancy between analysis and actual behavior is large, and any discrepancy obviously will lead to some complications in the actual behavior of the structure. If we are making a mistake in the analysis, obviously that will lead to a faulty design, and faulty design will lead to some problems later in the structure, obviously, that we know, right? So therefore, it is designed conservatively. What that means, that we are providing extra precautions. If the For example, if 10 bolts are required, I am providing 15 bolts. For example, that is conservative design. I am providing more than required, okay? Because I do not want the structure to fail at the joint. Why? Because different elements are connected at the joint. And if the joint fails, two, three connected members will fail. If there is a failure in an individual member, only that member is affected. I can call somebody and I can fix that. Okay. I can call the experts. I can fix that one single member. But if it fails at the joint, then two, three members may fail and it may be a catastrophic failure. So I do not want the structure to fail at their joint. Therefore, the joints are to be designed conservatively. They are to be designed with more care. Okay, so the connections are very costly. Okay, fine. So that is the importance of connection. We just saw the bolted connection. Then we will also be talking about riveted connections and welded connections after puja break. So that is enough for today. If there is anything, please tell me.